February 18, 1943, Bagot Peninsula, northern Russia. The earth trembled slightly as Lieutenant Colonel Viktor Komarov recorded the moment in his logbook. Words that would have seemed inconceivable just months earlier when experienced German tank commanders had openly questioned whether Soviet T-34s could navigate the spring thaw that transformed frozen terrain into impassable quagmires. We lose more tanks to mud than to enemy fire. Through the rain-spattered field glasses at the forward observation post, he had just watched his battalion's lead T-34 sink to its hull, its tracks spinning helplessly as it attempted to cross what appeared to be solid ground. The crew abandoned the 26-ton machine as it settled inexorably into the saturated soil, becoming another statistic in what Soviet commanders had begun calling General Mud's victories. The mathematics of battlefield mobility were being rewritten not in armor thickness or cannon caliber, but in the devastating physics of ground pressure, the relationship between vehicle weight and contact area that determined whether a tank advanced or became a stationary target. The T-34, despite its revolutionary sloped armor and exceptional firepower, exerted 11.8 pounds per square inch on the terrain beneath it. The heavier German Tiger tanks, at 12.7 pounds per square inch, fared even worse. Komarov watched as recovery vehicles themselves became mired attempting to retrieve the abandoned tank. The spring Rasputitsa, the seasonal mud that swallowed armies, had claimed another victim. His engineering officer, Captain Dmitry Vershinin, stood beside him, sketching calculations on a mud-spattered notebook. "The surface-bearing capacity is approximately 8.5 pounds per square inch," Vershinin muttered, "while our vehicles exert nearly 12. The physics is insurmountable without intervention." The transformation had begun months earlier, on September 8, 1942, when British engineer Reginald Allen submitted a classified report to the War Department analysing mobility failures during Operation Barbarossa and the North African campaigns. Allen's team at the Transportation Research Laboratory in Berkshire had meticulously documented the catastrophic impact of terrain on mechanized warfare. The statistics were sobering. During spring and autumn mud seasons in Russia, mobility-related losses accounted for 35% of all tank casualties. In North Africa, fine sand immobilized 28% of British armor during Operation Crusader. On the Eastern Front, over 2,300 German vehicles had been abandoned due to mud during the 1941-42 winter. The problem transcended nationality and theatre. It was the fundamental limitation of tracked vehicles designed for ideal conditions now operating in terrain that could not support their weight. Allen's engineering team had calculated the precise relationship between soil saturation, vehicle weight, and ground pressure. Their formulas, later refined by American engineers at the Aberdeen Proving Ground, demonstrated that even the most advanced suspension systems and widest tracks could not overcome basic physics when ground conditions deteriorated beyond critical thresholds. The soldiers called it different names: the Russian Rasputitsa, the Italian Fango, the Pacific Theater's monsoon quagmire. But the fundamental problem remained identical: how to prevent 30-ton machines from sinking into earth incapable of supporting such concentrated weight. At the Transportation Research Laboratory, Allen's assistant, Dr. Eleanor Westwood, had begun exploring unconventional solutions. Her background in textile engineering brought a different perspective to the problem. "If we cannot reduce the weight," she wrote in her October 1942 research notes, "we must dramatically increase the surface area over which that weight is distributed." The concept was simple in theory, but revolutionary in application. Temporary surfaces that could be deployed ahead of heavy vehicles to create artificial roadways with vastly improved load-bearing capacity. But the early experiments with steel matting had proved logistically impossible. The weight of the metal mats themselves required more transport capacity than was available in forward combat zones. The solution, when it finally emerged, would come not from metal, but from a material that military planners had previously dismissed as too civilian, too impractical for battlefield conditions: vulcanized rubber reinforced with complex textile structures. But that innovation remained months away as Lieutenant Colonel Komarov watched helplessly as 3 more tanks became immobilized, their crews abandoning them to enemy artillery that would soon target the stationary vehicles with devastating precision. December 4th, 1942, Berkshire, England. The table in Laboratory 7 at the Transportation Research Laboratory was littered with failed prototypes. Dr. Eleanor Westwood pushed aside a crumpled sheet of perforated steel, her frustration evident as she studied the weight calculation. 127 pounds per square metre of coverage, impossibly heavy for field deployment. The metal mats had seemed promising in theory, but proved disastrous in practice. Royal engineers testing the prototypes at Aldershot had reported that a single platoon required 3 additional trucks just to transport enough matting for 200 metres of makeshift roadway. "We're approaching this backward," Westwood muttered to her assistant, James Fordham. "Every metal-based solution creates a secondary logistics problem as severe as the original mobility issue." Skepticism had followed the project from its inception. General Montgomery himself had dismissed the concept as academic engineering with no battlefield utility after reviewing the first prototypes. Field commanders wanted wider tracks on existing vehicles, not additional equipment to transport. The breakthrough came not from the engineers, but from an unexpected visitor. Samuel Patterson, a civilian contractor who had spent 15 years developing conveyor belting for mining operations, noticed the failed prototypes during a tour of the facility on December 21st, 1942. "Your problem isn't the concept," Patterson observed, picking up a buckled steel sample. "It's the material. You're thinking like tank designers, not textile engineers." Patterson sketched a cross-section on Westwood's notepad. A flexible mat constructed from multiple layers of vulcanized rubber reinforced with rayon cord, similar to the pneumatic tires being manufactured for military vehicles but flattened into sheets. The composite material would weigh just 5.4 pounds per square foot, while distributing load across a much wider area. Initial calculations were promising. A 1 metre wide strip of the material could reduce ground pressure from a catastrophic 12.7 psi to a manageable 4.3 psi, well below the critical threshold for most saturated soils. The material's elasticity allowed it to conform to terrain irregularities, while its tensile strength, 11,500 pounds per square inch, prevented tearing under tracked vehicles. Fordham immediately recognized the potential. "If we create interlocking sections, each 2 meters by 1 meter, weighing approximately 10.8 pounds, a single truck could transport enough material to create 500 meters of temporary roadway." The textile reinforced rubber solution offered other advantages beyond weight reduction. The material provided superior traction in wet conditions compared to metal alternatives. It could be rolled for compact storage rather than stacked in rigid sections. And perhaps most critically, it utilized non-strategic materials, primarily synthetic rubber and rayon, that wouldn't compete with aircraft or ammunition production. By January 15, 1943, Westwood's team had fabricated the first prototype trackway sections. The manufacturing process involved precisely layered rubber sheets with diagonal fiber reinforcement at 45 degrees angles to provide multi-directional strength. Each section featured male and female interlocking edges that could be connected in seconds without tools. The prototype mat measured 2 meters x 1 meter x 3.8 centimeters thick with a distinctive diamond pattern surface for maximum traction. The material's specific gravity of 1.28 made it almost neutrally buoyant, an unexpected benefit discovered when Fordham accidentally dropped a section into the laboratory's test tank. Initial testing using a 9-ton universal carrier produced encouraging results. The ground pressure under the vehicle decreased from 8.2 psi to 3.1 psi when driving over the prototype mats. More importantly, the vehicle successfully traversed a test pit containing soil with a bearing capacity of just 4.7 psi, conditions that had previously caused immediate immobilization. The early prototypes weren't without flaws. The rubber compound degraded rapidly in extreme cold, becoming brittle below 18 degrees. The joints failed under repeated passes of vehicles above 22 tons, and the production process required specialized vulcanizing equipment not readily available in wartime Britain. But Westwood recognized they had found the fundamental solution. Her February 2nd report to the Ministry of Supply stated with characteristic restraint, "We have identified a viable approach to the mobility challenge that warrants accelerated development." The understated language concealed what would soon become one of the war's most transformative engineering innovations. Field testing would reveal whether this academic solution could survive the brutal realities of combat deployment. The prototype mats were packed for shipment to the 79th Armored Division, where they would face their first genuine battlefield evaluation on terrain far less forgiving than laboratory test pits. March 17, 1943. Aberdeen Proving Ground, Maryland. The rubber mat buckled visibly as the M4 Sherman tank crawled forward. Captain Robert Winters winced, expecting the catastrophic failure that had plagued previous iterations. The tank's 30.3-ton mass concentrated enormous pressure on the experimental surface. A modified version of Westwood's design reinforced with nylon rather than rayon. The material held, distributing the tank's weight across its engineered surface, but the deformation exceeded acceptable parameters by 13%. "Too much elasticity in the polymer matrix," noted Dr. Howard Garrett, scribbling observations in his field journal. The American team had been working to adapt the British concept since receiving Westwood's preliminary designs in January. The US Army's requirements were more demanding, their vehicles heavier, the expected terrain conditions more varied, and the production requirements measured in square miles rather than meters. The primary challenge had shifted from concept to execution. The basic principle, distributing ground pressure across artificial surfaces, had been validated, but transforming laboratory prototypes into battlefield-ready systems revealed new complications daily. Material shortages presented the most immediate obstacle. Natural rubber supplies had been cut off when Japan captured Malaya and the Dutch East Indies. The synthetic alternatives, GRAS, government rubber styrene, and thiocol, displayed inferior tensile strength at just 4,200 pounds per square inch compared to natural rubber's 6,800. This necessitated thicker mats, which in turn increased weight and reduced transportability. The reinforcing textiles posed another dilemma. Tests revealed that cotton deteriorated rapidly when exposed to moisture, while nylon and rayon remained scarce due to parachute production requirements. Garrett's team experimented with fiberglass reinforcement, achieving impressive strength at 22,000 pounds per square inch, but with concerning brittleness under repeated flexing. Temperature performance created additional complications. The original British compound became rigid at 14-degree Celsius, making it unusable in winter conditions. The American GRS formulation maintained flexibility to 4 degrees, but softened excessively above 95 degrees, compromising load-bearing capacity in desert environments. "We need a compound that functions from North Africa to Norway," Garrett explained to visiting observers from the Quartermaster Corps. His team had developed a modified polymer incorporating chloroprene, neoprene, that maintained operational characteristics from 20-degree currents to 120-degree currents. But production costs increased by 340%, an unacceptable trade-off given the quantities required. Testing protocols evolved to match battlefield conditions. The Aberdeen engineers constructed specialized chambers to simulate Russian mud, North African sand, and Pacific Island swamps. They developed the progressive failure test, subjecting each prototype to repeated passes of increasingly heavy vehicles until the material reached breaking point. Two competing designs emerged by late March. The T8 Marsden mat utilized a semi-rigid rubber compound reinforced with bidirectional nylon cording at 90 degrees angles, creating a lattice structure within the material. It performed exceptionally well under tracked vehicles, but showed accelerated wear patterns from the turning forces of wheeled transport. The alternative T9 trackway employed a more flexible formulation with diagonal reinforcement at 60-degree angles, creating a triangulated internal structure. This design distributed weight more effectively across soft terrain, but suffered from reduced durability, lasting through approximately 370 vehicle passes compared to the T8's 520. The breakthrough came on April 2nd, when metallurgist Dr. Elaine Simmons suggested incorporating thin, flexible steel wires within the rubber matrix, a hybrid approach that combined the weight advantages of polymer construction with the strength of metal reinforcement. The resulting T11 prototype achieved remarkable performance metrics: 85% weight reduction compared to steel matting, load capacity of 44 tons, temperature stability from 30-degree Fahrenheit to 130-degree Fahrenheit, and durability exceeding 700 vehicle passes. Production remained the final hurdle. The manufacturing process required precise alignment of reinforcement elements during vulcanization at 287 degrees Celsius for exactly 42 minutes. The specialized presses needed were already committed to aircraft tire production. Engineers at Firestone developed a continuous vulcanization method that increased production capacity to 4,800 square meters daily, still far below the projected battlefield requirements. By late April, the team had achieved a viable compromise: the T-13 system combining moderate performance with simplified production methods. The finalized design featured interlocking sections measuring 2 meters by 3 meters, weighing 42 pounds each, with a load capacity of 38 tons. The compound remained stable across all projected theater temperature ranges while utilizing materials that didn't compete with critical war production. The success came just as field reports from Tunisia described entire tank battalions immobilized in seasonal rain, their offensive capability neutralized not by enemy action, but by terrain. The engineers' race against physics was becoming a race against the advancing Allied timetable. June 11th, 1943, Salisbury Plain, England. Rain fell in sheets as the convoy of Sherman tanks approached the test area. Major William Harrison of the 2nd Armoured Division stood alongside British Colonel James Sutherland, both men watching intently as the lead vehicle approached the deliberately flooded depression. Previous attempts to cross this section had resulted in tanks sinking to their turrets in the saturated clay soil with a bearing capacity of just 3.2 psi. "This is where we lost 3 yesterday," Harrison commented, gesturing to the recovery vehicles still extracting the final bogged-down Sherman. Advanced teams had deployed the T-13 trackway system across the 120-meter stretch, creating an artificial roadway of interlocking rubber mats. The process had taken 24 soldiers, exactly 38 minutes, significantly faster than predicted. Each 2-man team carried a single folded mat section, weighing 42 pounds, deploying and connecting them in a continuous sequence. The lead Sherman approached at 8 mph, its 30.3-ton mass concentrated on tracks exerting 13.7 psi of ground pressure. As it reached the matted section, the pressure dispersed across the engineered surface, effectively reducing ground contact to 4.1 psi, safely below the soil's failure threshold. The tank crossed without hesitation, followed by 5 more vehicles at 30-second intervals. "Bloody marvellous," Colonel Sutherland muttered, making notes in his waterproof field book. German intelligence reports later captured near Caen revealed their assessment of the new technology. Allied forces have deployed synthetic road surfaces, enabling armour to traverse previously impassable terrain. This capability significantly threatens our defensive strategy of channeling enemy advances through predetermined corridors. The trackway system's most impressive performance came during Operation Goodwood, when British armour needed to cross marshy ground near the Orne River. Combat engineers from the 79th Armoured Division deployed 1.8 kilometres of trackway in under 2 hours, creating stable crossing points that allowed 240 vehicles to traverse terrain with soil-bearing capacity as low as 2.8 psi. Performance metrics exceeded expectations across all evaluation criteria. Vehicles up to 42 tons crossed successfully. The mats withstood 812 vehicle passes before requiring replacement. Deployment speed averaged 41 meters per minute with trained teams. Most significantly, vehicle mobility increased by 64% across previously impassable terrain types. The system underwent continuous refinement based on field experience. The Mark II version, introduced in August 1943, featured improved connector designs that reduced deployment time by 23%. The material composition shifted to incorporate higher percentages of reclaimed rubber, reducing production demands on strategic materials by 38%. By September 1943, factories in Britain and the United States were producing 12,400 square meters of trackway daily, enough to create 41 kilometers of temporary roadway per month. The technology had transformed from experimental concept to standard battlefield equipment in less than 1 year, an extraordinary feat of wartime engineering and production. August 24, 1943. Falaise Pocket, Normandy. The statistics told a story more compelling than propaganda. 3 armoured divisions had advanced 11.4 kilometres in 6 hours across terrain that German commanders had classified as Type Waffe impassable to tracked vehicles in their defensive planning. The rubber trackway system, now designated M1938 by American forces and trackway Type F by British units, had been deployed in unprecedented quantities, 4,800 metres in a single day along 3 parallel advance routes. Lieutenant General George Patton, initially sceptical of the rubber road concept, personally witnessed its effectiveness during the breakout from St. Lo. His after-action report noted, "The mobility advantage provided by trackway deployment transformed what would have been a frontal assault through predictable corridors into a multi-pronged advance that German forces could not adequately counter." Tactical surprise was achieved not through deception, but through previously impossible maneuver capability. Production had scaled dramatically through streamlined manufacturing processes. The Firestone plant in Akron, Ohio produced 8,400 square meters daily. British factories in Manchester contributed another 4,200 square meters. By September 1943, total production reached 378,000 square meters monthly, enough to create 1,260 separate vehicle crossing points across previously impassable terrain. Deployment tactics evolved through battlefield experience. The 291st Engineer Combat Battalion perfected the rolling deployment method, allowing continuous trackway installation while under sporadic artillery fire. The technique involved armoured personnel carriers modified to carry pre-connected trackway sections that could be unrolled from the rear of moving vehicles, creating usable roadway at rates approaching 120 meters per minute. The German response proved ineffective. Artillery barrages targeting deployed trackway caused minimal damage to the flexible rubber material. Captured documents from OKW headquarters revealed a desperate directive to construct additional fixed defensive positions after acknowledging, "Allied trackway systems have neutralized our terrain-based defensive strategy. Previous natural obstacles no longer channel enemy movements predictably. Operational statistics confirm the system's impact. Tank battalions using trackway support achieved 87% of planned advance rates in adverse terrain conditions compared to 34% for unsupported units. Fuel consumption decreased by 41% when vehicles traversed prepared surfaces rather than struggling through mud. Maintenance requirements for suspension components dropped 56% as tracked vehicles encountered fewer extreme stress conditions. The doctrine of mechanized warfare underwent fundamental revision. General Omar Bradley's tactical memorandum of October 1943 stated, "Engineering preparation now precedes rather than follows armored advance. terrain previously considered impassable is now classified as delayed transit requiring trackway deployment. No natural surface condition short of vertical elevation should be considered a permanent obstacle to mechanized forces. The most dramatic demonstration came during the Ardennes counteroffensive in December 1944. German forces, lacking comparable mobility systems, found their heavy panzer divisions channeled into predictable routes by snow and mud. American forces, despite initial setbacks, rapidly deployed trackway systems enabling flanking maneuvers through forested areas previously considered impassable to armor. The resulting encirclement accelerated the German retreat and shortened the campaign by an estimated 14 days. May 3, 1945, Rhineland, Germany. The rubber mat rested in a museum display case, its surface worn by the tracks of hundreds of vehicles that had crossed from the west bank of the Rhine to the east on March 7, 1944. The small identifying plate noted M1938 Trackway Section, 9th Armoured Division, Ludendorff Bridge Approach. The once revolutionary technology had become standard equipment, its presence expected rather than remarkable in combat engineering operations. Colonel Herbert Vogel of the Army Corps of Engineers studied the display with professional interest. The trackway system altered not just mobility, but the fundamental relationship between terrain and tactical planning, he noted to the assembled officers. Defensive strategy predating 1943 assumed fixed terrain coefficients that no longer apply. The statistics supported his assessment. Allied forces had deployed 2.86 million square meters of trackway during the European campaign, creating 9,533 kilometers of temporary roadway across terrain previously classified as impassable. The system had enabled 14 major offensive operations that German planning had considered impossible due to ground conditions, including the crucial Seine River crossing, where boggy approaches had been transformed into stable transit corridors in less than 3 hours. The technology transitioned to civilian applications with remarkable speed. By August 1945, modified trackway systems were being manufactured by 17 companies for non-military purposes. The petroleum industry adopted the technology for exploration in Alaska's tundra, where vehicles exerting more than 4.8 psi of ground pressure were prohibited by environmental regulations. The M1945 commercial trackway reduced contact pressure to 1.7 psi while enabling equipment weighing up to 28 tons to operate on fragile ecosystems. Construction firms discovered the system's value for operating in wetland areas, soft coastal soils, and during seasonal thaws when conventional equipment would otherwise sink. The International Harvester Company integrated similar technology into agricultural applications, allowing earlier planting and later harvest in regions with marginal soil conditions. The engineering principles established during wartime development evolved into fundamental concepts in ground pressure management. Modern highway construction incorporated distributed load principles, first documented in Dr. Westwood's 1943 papers. The road-based materials developed for the interstate highway system utilized multiple compressible layers that functioned on identical physical principles. Technical specifications evolved dramatically in the post-war period. The original M1938 material, with 4,200 psi tensile strength, was superseded by advanced polymer composites achieving 21,000 psi. Weight decreased from 5.4 pounds per square foot to 1.8 pounds through carbon fiber reinforcement. Temperature tolerance expanded to 60 degrees Celsius through 160 degrees Celsius with the introduction of silicone-modified compounds. Contemporary versions produced in 2025 bear little visual resemblance to their wartime predecessors, but operate on identical physical principles. The Rapid Deployment Surface System used by the US military incorporates nanomaterial reinforcement within a self-healing polymer matrix, reducing weight to 0.86 pounds per square foot while supporting vehicles exceeding 70 tons. February 18, 1943, had witnessed Lieutenant Colonel Komarov's T-34 sinking helplessly into Russian mud, triggering the engineering revolution that transformed mobility doctrine. 82 years later, MBT-84 Abrams tanks crossed terrain with 13% water content at full tactical speed, their ground pressure effectively managed by descendants of those first experimental rubber mats. The fundamental problem remains unchanged. Heavy vehicles sink when ground pressure exceeds soil-bearing capacity. The solution remains equally consistent. Distribute weight across engineered surfaces that transform point pressure into manageable distributed loads. What began as desperate wartime improvisation has evolved into standard engineering practice, enabling movement across terrain that physics would otherwise render impassable.